today's lesson, we're going to be asked questions about buffers. And when you have a weak acid being titrated by a strong base, if you're at the equivalence point, then the pH is going to be affected by the conjugate base of the weak acid. If, on the other hand, you have not reached equivalence, if you're somewhere before equivalence, you have a buffer system. In this question, we're asked to calculate the pH of the solution at the equivalence point, which means just enough base has been added to a solution of benzoic acid so that all of the benzoic acid has been titrated. And then what happens is the benzoate anion abstracts the proton from the water, which is the solvent in this case, and lowers the pH as a result. Actually, no, it raises the pH, sorry. It would put the pH into the basic side of the spectrum, above 7. So the first step in solving this problem, we're told that 40 mL of 0.025 molar benzoic acid is titrated with a 0.05 molar sodium hydroxide solution. First step is to find out how much benzoic acid we had, which we do here. 41 thousandths of a liter times the molarity of the benzoic acid tells us we have 1.0 times 10 to the minus 3 moles of, I called it HB, so that we don't have to redraw this whole molecule. Therefore, we need the same number of moles of sodium hydroxide to titrate the benzoic acid. And because our solution is 0.05 molar, we're going to find out how many liters of solution are necessary. Notice that the number of moles is equal to the molarity times the volume. So I've rearranged the equation to solve for the volume of sodium hydroxide needed of this concentration to titrate this much benzoic acid. So it turns out we need 20 mL of sodium hydroxide solution. Now when you do a titration, you're adding one solution to another, so that's going to affect the volume. The total volume is going to be 40 plus the amount of titrant that was added. So the total volume is going to be 60. And that's where we calculate what the concentration of the benzoate anion is going to be. We're going to produce 1.0 times 10 to the minus 3 moles of benzoate anion, and the new volume of the solution is going to be 60 1,000ths of a liter. So the concentration of benzoate is going to be 1.6 recurring times 10 to the minus 2. We also need to find the Kb value for benzoate, because we're only given the Ka value. So you do that by dividing Kw by Ka to find Kb, or vice versa, we can flip those two quantities. And it turns out the Kb for the benzoate anion is 1.58 times 10 to the minus 10. We then set up an ice table, if necessary. X amount of benzoate is going to react with water, abstracting a proton, resulting in the formation of benzoic acid and some hydroxide anions. We set up the equation where X times X over product, so it's HB, the benzoic acid times hydroxide concentration, over the benzoate anion concentration. That is how we set up our equilibrium. Let's write that down to remind you. Kb is established this way. So that's what these values that we've substituted into the ice table represent. I've also made the assumption that the value of X is going to be much smaller than the concentration of the benzoate anion. So it's safe to make this assumption, I think. And we're going to test it out anyway by doing an iteration. The value of X I get when I solve for X here is 1.62 times 10 to the minus 6. And then what I did is I took that number and I placed it into the original equation, into the minus X part, and recalculated the value of X, and it gave me a number that is hardly different from the original value. So because there's no appreciable change, there's no need to do any more iterations. You're going to get this number. It's basically very close to the actual value. That it represents the concentration of hydroxide ion. We put that into the pOH equation. It gives us a pOH of 5.79, and 14 minus the pOH will tell us the pH of the solution, 8.21. And it stands to reason that we should have a pH above 7 because the benzoate anion should be basic. In the next example, which is part B of the same practice exercise in brown, 40 mL of a 0.1 molar solution of ammonia is titrated with 0.1 molar hydrochloric acid. Same setup, except now we're starting with a weak base and we're titrating with a strong acid. We find out how many moles of ammonia we have by multiplying volume of the solution times the concentration. We find out that we have 4.0 times 10 to the minus 3 moles of ammonia, which is going to require the same number of moles of hydrochloric acid. We're given the concentration of the hydrochloric acid and we're given the number of moles, so we can find the volume of the solution necessary. It turns out to be 0.04 liter. Now the total volume of the solution post-titration will be the 40 ml, will be given by the 40 mLs of the hydrochloric acid that was added, plus the 40 mLs of the ammonia solution that we had originally. So the total volume will be 80 mLs, or 0.08 of a liter, and that's going to be necessary to calculate the ammonium ion concentration. Here's the amount of ammonium, here's the volume of the solution, there's the concentration of ammonium. So at equivalence, ammonium is the only species present that dissociates to release protons, and we have to calculate the value of Ka for ammonium. We're only given the Kb of ammonia, so we put it into Kw. Kw divided Kb gives us Ka. The Ka for ammonium is 5.5 recurring times 10 to the minus 10. We set up the regular ice table, where the value of X, we let X equal the amount of hydronium ion that forms from the presence of ammonium. And amount of X of ammonium will disappear. So at equilibrium we'll have 5.0 times 10 to the minus 2 minus X of ammonium. The ammonia concentration will have increased from 0 to X, and the hydronium concentration will have increased from 0 to X. We set up the equation Ka is equal to this number, which we calculated earlier, and that equals X squared over 5.0 times 10 to the minus 2 minus X. Again, we can make the approximation that the value of X is way less than 5.0 times 10 to the minus 2. And we judge that by the fact that the value of Ka is a very small number. We get a value for X using this approximation. And then just to make sure, we plug in this value of X back into the original equation to see if it makes a difference. And it doesn't really make an appreciable difference. So we stick with this value. pH is equal to the negative log of H plus concentration, which is what X represents, hydronium or H plus. And the pH comes out to 5.28. And again, it stands to reason because when you have a weak base being titrated by a strong acid, the result is that the conjugate acid is a weak acid itself, and it should lower the pH to below 7.